the speaker. No. Okay, good morning, everyone. I'd like to get started very promptly this morning for reasons that will become apparent. My name is Jim Hurl, and I have the pleasure of serving as the president-elect of the Atmospheric Science section of AGU. And it's my pleasure to welcome all of you to the 2017 Bjerknes Lecture, named in recognition of the foundational contributions he made to the atmospheric sciences. This morning, it's my honor to introduce my colleague and my friend, Dr. Clara Desser, as this year's Bjerknes Lecturer. Unfortunately, Clara was unable to travel to New Orleans this year for medical reasons, but she has pre-recorded her presentation, and she is online listening and watching. And the reason I want to get started promptly is so that we have at least a few minutes at the end of her presentation to ask questions, at least a couple of questions. Clara holds the position of a senior scientist at the National Center for Atmospheric Research in Boulder, NCAR, where she leads our climate analysis section. Clara's research spans a very broad range of topics within the field of climate variability and climate change research, and her work has combined both observational analysis and climate modeling approaches in very novel ways to study the interactions among the different components of the climate system. Her work has been communicated in over 150 peer-reviewed publications. As a result of her body of work, she has received many prestigious awards and recognitions from professional societies, including fellowship in the American Geophysical Union. In addition to her research efforts, for those of you that know Clara, you know she spends considerable time mentoring graduate students, postdocs, and early career scientists. She also leads a number of community-oriented projects, some of which we'll hear about today. So please join me in welcoming and congratulating Clara Desser as this year's Bjerknes Lecturer.
Thank you all for coming today, and I'm very sorry I was unable to be with you in person. I'm truly honored to have been asked to give the Bjerknes Lecture at AGU. So today I would like to talk about new perspectives on the role of internal variability in regional climate change and climate model evaluation. I have many people to thank who have contributed to this talk, including Adam Phillips, the model development team at NCAR and beyond, and many colleagues who have contributed to this work. So the topic really is anthropogenic climate change in the presence of internal climate variability. And we will address two overarching questions today. The first, how do we disentangle anthropogenic influences from internal variability at local and regional scales? And secondly, how do we evaluate climate model projections at these scales, given the noise from internal variability? These questions were called out in the IPCC reports as outstanding challenges, in particular spatial scales less than continental and time scales less than 50 years. So the story I'd like to tell you about today in a nutshell. First, that the atmospheric circulation plays a central role in inducing internal climate variability, even on timescales as long as 50 years. Secondly, this internal variability confounds attribution and model assessment and it causes irreducible uncertainty in climate projections because of its unpredictable nature. Despite these difficulties, there are several paths forward. The first includes the use of large model ensembles. The second is a technique called Dynamical Adjustment. And finally, observational constraints can be brought to bear to unravel these questions. And we have made many strides forward in the last 5 years or so on these various ways forward. So the outline of the talk. First, I'll give a broad overview of internal climate variability. Then we'll discuss how to make sense of climate model projections. Third, we'll spend some time discussing how to remove the atmospheric circulation effects to better reveal the anthropogenic response in surface climate. And fourth, we'll discuss observational constraints and limitations in the observational record. And then I will conclude with a summary and an outlook. So first, internal climate variability is ubiquitous. It abounds. And this variability owes its existence to processes internal to the atmosphere, coupled processes between the ocean and the atmosphere, and then processes intrinsic to the ocean. So if we first look at the atmospheric internal variability, we can think of this as weather. This is day-to-day, week-to-week fluctuations in our weather. And I give an example here from the winter of 2015, which showed record cold in the eastern half of the U.S. and record warmth on the western half. So the country was truly divided. And this pattern lingered for an entire month, and it was due to the path of the jet stream shown on the left-hand side of the screen, where we had a strong ridge on the west coast of the U.S. and then a very deep low on the east coast, bringing unusually cold temperatures. So this weather variability, of course, is very limited in its predictability, typically in mid-latitude, something less than a few weeks. However, that does not mean that fluctuations don't occur on longer timescales. In fact, the atmosphere is a chaotic, nonlinear dynamical fluid, and it behaves as a random stochastic process on timescales longer than about a month. And so this produces variability on all timescales, including decadal and centennial, and even longer. And of course, this nonlinear dynamics is not predictable on these longer timescales. So let me just show you an example of the type of long timescale fluctuations intrinsic to the atmosphere. So again, coming back to jet stream variability, in this case I show you an example for the southern hemisphere, the leading mode of interannual variability called the southern annular mode, sort of a wobbling of the jet stream, if you will. And this is a power spectrum, and the black curve shows you from 30 years of observations, and you can see that have sort of a characteristic spectrum where it's red noise on timescales less than about 60 days, and then weekly red noise, almost white noise, on timescales longer than a year. The gray curve shows you a simulation from an atmospheric general circulation model, so no coupling with the ocean or any other component of the climate system. And this simulation was run 200 years, and it shows a very nice match to the observed record over the timescales of overlap. And then you can see that on the longer timescales, we continue to have variability, although there are no dynamical processes acting on these timescales. It's just a remnant of the variability that is acting on shorter timescales. So this is a very important concept that I'll come back to throughout the talk. So secondly, coupling between the ocean and the atmosphere gives rise to a whole host of phenomena that would not otherwise exist. Madden-Julian oscillation on intraseasonal timescales, El Nino Southern Oscillation on interannual, and then the two leading modes on decadal and multidecadal timescales, the interdecadal Pacific Oscillation and the Atlantic multidecadal oscillation. So ENSO is probably the prime example of coupled ocean-atmosphere interaction. And of course, the namesake for this lecture series, Csf Bjerknes, was one of the pioneers in providing physical insight into the coupling between the El Nino ocean side of the phenomenon and the southern oscillation atmospheric side. So this is just a record of the sea surface temperatures in the heart of the ENSO region in the eastern equatorial Pacific. And we see examples of El Nino and La Nina events occurring on timescales something like 3 to 5 years. The predictability of this phenomenon is limited to 1 to 2 years, and some references provided as you see. And an example of the longer timescale fluctuations, the Atlantic multidecadal oscillation. This is a record of sea surface temperatures in the North Atlantic, beginning in 1900 to present, very prominent multidecadal fluctuations, even in monthly data. Again, it looks like a regular cycle, but predictability is limited to something like a decade at present. Finally, the ocean has its own intrinsic dynamical variability. This can arise from mesoscale eddies, also the thermohaline circulation, also known as AMOC, the Atlantic meridional overturning circulation. So collectively, these phenomena of internal climate variability have, as depicted here, you can think of their predictability time horizons something like weeks for weather, up to a decade for the Atlantic multidecadal oscillation. Recent nice summary in Williams et al. JGR paper. And so beyond the predictability timescale, it's maybe useful in some sense to think of the internal variability as a roll of the dice. In other words, we really don't have any ability to predict their fluctuations beyond about a decade at best. So beyond that time scale, it's really unpredictable rolling the dice. So of course, on local and regional spatial scales, climate change is really a combination of these internal fluctuations and the effects from anthropogenic climate change. And these two influences coexist. And because the internal variability can have long time scales, sometimes it is very difficult to unravel their influences, and they're often confounded and misinterpreted because these two influences do coexist. So, secondly, I'd like to talk about making sense of climate model projections, and I want to specifically focus on insights from a large ensemble with one climate model, the NCAR Community Earth System Model, version 1. It's the most recent version of the model. We're getting ready to release version 2 in just a few weeks here. So this is referred to as CESM1. It's a global, coupled, state-of-the-art general circulation model of the climate system. This has 1 degree latitude by 1 degree longitude spatial resolution. So as such models go, it is actually quite a fine resolution model of the Earth's climate system. And I will also be discussing the CMIP3 and CMIP5 archives as we go on in the talk. So what is the CESM Large Ensemble? This was a project put together by the community, spearheaded by many of us at NCAR, and this is a project to study climate change in the presence of internal climate variability. This is a set of model simulations, as I will describe in the next slide, and our intent was to make them as widely relevant and accessible by the community at large. And so we have many resources as described on this website for those of you interested in replicating the experimental design, diagnostics from the model simulations, and also data sets available to the community, and a whole list of publications. In fact, since its publication in mid-2016, there have already been 315 citations to date in the peer-reviewed literature, giving you some idea of the utility of this large ensemble project to the community at large. So next I'll describe the simulations in a little bit of detail as they will be important as we go on in the talk. So the CESM1 Large Ensemble project, as I said, is a collection of model simulations. It begins with a pre-industrial control run under 1850 radiative forcing conditions, and that control run was run for many hundreds of years to ensure that the climate system state was in fairly quasi-equilibrium stable state. And then after 400 years, we began the so-called historical forcing runs. So from 1850 all the way to 2100, and so for the historical portion, it's subject to the typical radiative forcing protocols, that is, changes in volcanic activity, solar insolation, greenhouse gases, black carbon, and the like. And then from in the future portion of the segment, subject to the RCP radiative concentration pathway 8.5, meaning that the radiative imbalance at the end of the century is 8.5 watts per meter squared. Then in 1920, we launched 41 additional ensemble members. These begin from the identical states of the first ensemble member on January 1st of 1920, with one exception, and that is in the atmospheric model component. We perturb the atmospheric temperatures at the level of round-off error, meaning 10 to the minus 14th degrees Kelvin. So imperceptible, random changes to the atmospheric temperatures. That is the quintessential butterfly effect. That creates spread, serves to create spread amongst each ensemble member. And as you will see, it plays out in the sense that each ensemble member will have a different sequence of internal variability because it is not predictable beyond this time scale of about a decade, as I showed you in the first part of the talk. So the spread is unpredictable after about 1930, and each ensemble member has a unique history of internal variability superimposed upon the identical forced response. I'm showing radiative forcing as a hammer. That's the strong forcing that's applied to each one of the simulations. So the key here is that each simulation undergoes the same radiative forcing, it's conducted with the same model, and then imperceptible initial condition perturbations to the atmospheric component. So here's a graph showing you the global mean surface temperature anomalies for the control run in blue, then the first member in black that begins in 1850 and goes all the way to 2100. And then the spread amongst the 42 members, they're all shown in gray. And then the observations are shown in the red curve. And you can see on the global mean scale, the model actually tracks the observed record very well. We're not expecting any identical match because the internal variability can have a different sequence from that in the observations. This is not the first large ensemble. The ECM5 model and the CCSM3 model also conducted large ensembles, but this is the largest one to date with the newest version of the NCAR climate model, and it's also the one for which the model output has been made widely available to the community. So what I'd like to show you next are linear trends over the next 50 years in northern winter, where we average the months December, January, and February. So we fit linear trends to the data at each grid box, and the linear trend is reasonable for the next 50 years, as you can see from the global temperature record. So here I'm showing you the first 9 members of this 42-member ensemble. I'm showing you the linear trends in the sea level pressure field from each one of these members. And blue colors denote pressure falls or a negative trend, and red shades denote increases in pressure over time. And I'll just point out a few features. For example, these are global maps. Here we're zooming in on the North Atlantic within these circles, and you can see that the North Atlantic oscillation, this dipole between the north and the south, can take on the opposite polarity in individual members. If we look at the southern hemisphere, again, this southern annular mode, the dipole between the mid-latitudes and the polar region, can also have opposite polarities in individual members. And finally, we look at the North Pacific. We can have deepening of the Aleutian low, or we can have a ridge forming over the North Pacific. So we have very different behavior in each one of these members, and that attests to the relative strength or prominence of the internal variability compared to forced response. This is the same depiction of 50-year sea level pressure trends in the future, but from 9 of the CMIP5 models. So these are 9 models. They're just alphabetical, just calling them Model 1, 2, etc., but they're the first 9 models in alphabetical order in the CMIP5 archive, also for the RCP 8.54. And the color scale is just the same as what you saw a moment ago. And again, we can find instances of opposite pressure behavior in the North Pacific between models, also in the southern hemisphere, opposite behavior, and finally in the Atlantic, opposite behavior. So when you only have one simulation from each model, it's impossible really to separate the influence from internal variability versus differences in how the models are constructed. So these two sources of uncertainty are confounded. They are inextricable when you only have one member or even just a few members, simulations for each model. And that is largely the case in the CMIP archive. Most models only have a few simulations. So these two sources of variability are confounded. So if we take all of the models in the CMIP archive and all of the simulations from the CESN1 large ensemble, and we can form the standard deviation of these sea level pressure trends. So just the standard deviation of all of the maps that I've just shown. And we can compare the two types of model ensembles. On your left is the CESN1 42-member ensemble. That's the standard deviation of trends due to internal variability by definition. And then you have the CMIP models, one run each from 38 of the different models. Again, internal variability and model differences contribute to these. The stippling shows you where these two sets of distributions are different at the 5% significance level according to F-test. And the stippling is really only in the tropics. and at high latitudes of the southern hemisphere. But throughout the mid-latitudes, the extratropics of the northern hemisphere, these two distributions are not significantly different from one another. And indeed, internal variability accounts for most of the spread, much of the spread, within the CMIP5 archive. And again, the important thing here is that on this 50-year time scale, spread due to internal variability is unpredictable and therefore irreducible. So if we think about climate change, it's really a signal-to-noise problem. We're interested in how the anthropogenic influence affects the mean climate state, but this, of course, is against the noise from internal variability as well as model differences. So really, the quantity of interest here is the ensemble mean trend. That's telling you the forced signal, because each ensemble member's internal variability has a random sequence. And so when you have enough members, this sequence is averaged out, and you are left with the forced signal due to the greenhouse gas increases. And then we divide that by the standard deviation of the trends that we saw a moment ago, and we can form maps then of signal to noise. So that's what I'm showing you here in this slide, the signal to noise of these 50-year trends in sea level pressure, again from the Csf Large Ensemble and the sea. And you can see the color scale here in the northern high latitudes. Most of the values are actually less than 1, particularly for the CMIP archive, but also for much of the region in the Csf Large Ensemble. This means that anthropogenic effects will be very difficult to detect in the sea level pressure field, and it also means that any individual simulation, sea level pressure trends, are mainly unforced. That is, they are internal to the climate system and not a consequence of the anthropogenic relative forcing. This point has also been made in a Shepard paper and Trenberth et al., also relevant to much shorter timescales than I emphasize here. Okay, so what are the effects or the impacts of this internal atmospheric circulation variability on surface climate change projections? I just show you an example for North America, looking at the air temperature trends in the wintertime for the next 50 years, but we get very similar results when we look at Europe and Asia as well. So here is an example. It's actually from the previous large ensemble with CCSM3, but I assure you very similar results are found for the CESM large ensemble. So here I picked out 2 of the runs. I'll call them Run A and Run B. And I'm showing you in the contours the sea level pressure trends just for the specific North American domain, and also showing you the air temperature trends in the color shading here. And you can see Run A features a ridge over the North Pacific, that is a trend over the next 50 years for more rigid, and that causes cooling over the far western part of the continent, indicated by the blue arrow. Run B has pretty much the opposite sea level pressure trend, despite that it's also subject to the same increase in greenhouse gases. And this causes a lot of warming due to the flow of southerly maritime air coming into the continent. So, how do we unravel the influence on the air temperature field? Well, in a model ensemble such as this, it's very easy. We compute the ensemble mean, and that gives us a good estimate of the radiatively forced component, as long as you have enough ensemble members, and these papers give you some indication how many are needed. So here I show you the ensemble mean sea level pressure trend, as well as the air temperature trends on the same scales as for the total field. The first thing to note is that the force trend in sea level pressure, it is present, but it is much weaker than the trends in any of these two individual members. And the second is that there's a very simple pattern of increased warming as you go towards the Arctic part of the continent. This is a well-known consequence of Arctic amplification, of having more warming towards the north. If we subtract the force component from the total, by definition we get the internal, or the internally generated component of the trends. And again, this is depicted as this butterfly effect. And here we see the internal component. Again, the sea level pressure trends are primarily internal, and they give rise to very large-scale patterns of air temperature trends. These are really continental scale patterns, and their amplitudes can rival, in many locations, the amplitude of the force response. So it's very important, then, influence on the sea level, on the trends coming from the atmospheric circulation. So as I said, we have many examples also for Eurasia and also for precipitation. I won't show those here. An important facet here is when we think about downscaling with regional climate models, we really have to make sure we are accounting for this global scale internal variability of the atmospheric general circulation. So we need to make sure that at the lateral boundaries of our regional climate models, we specify these changes from the global scale models. And I'll show you some work in progress that we've done at NCAR. The Canadian group led by John Fife also has a very nice paper, just can't come out on similar regional downscaling. So here's an example with the WRF model, which is a 20-kilometer resolution model for the western U.S. And here we have forced the model at the lateral boundaries with two of the large ensemble runs from the CESN1. And this is showing you the effect on wintertime precipitation. This is the change in the 2070s relative to present day. You can see that you get very different conditions. Wetting on the west coast for member 2, and then kind of a dipole pattern of wetting and drying to the north and south on the west coast for member 30. So this is very important consequences also for regional downscaling. Okay, now I'd like to spend some time on the third aspect, which is, I think, a very promising way forward, and we call it dynamical adjustment. And it really means that we're trying to, in some sense, remove or at least reduce the effects of internal atmospheric circulation variability from the surface climate anomalies as a way of revealing the forced climate response, the radiatively forced climate response. This dynamical adjustment notion or concept has a long history. Wallace et al. In the 1990s have many papers, just one example here, and other papers since then showing the real power of this technique. Here, so in a nutshell, dynamical adjustment is a way of finding the circulation-induced component to a particular temperature anomaly field. And then once you have that, you can then back out the residual thermodynamic component by subtracting it from the actual temperature anomaly. So here, what's new here is the actual procedure, which has been improving over time, and I'm sure there's still more improvements to be made in the future. It has been conducted with several methods, including partial least squares regression, constructed circulation analogs, and also an EUF approach. And in all of these, the idea is that you use the entire data record, as long of a record as you have, to find the temperature anomaly that is on average associated with a particular circulation anomaly. Once you have found that average pattern, then you can find that, then you can scale that pattern with the actual circulation anomaly that obtains in any particular month and year, and thereby finding the dynamically induced or circulation-induced component. So here I'll show you two ways that we've applied dynamical adjustment. First is you can test the efficacy of this procedure with a large ensemble where you know the true forced response, which equates to the ensemble mean. And then once you have how well the method works, you can apply it to the observations to get at the question of attribution. So I'll show you here an example from simulation number 7 from the CSM Large Ensemble. I picked this one out because it actually has the most trends that are most similar to the observed trends over the last 50 years, and I'll show that to you in a moment. So this first is a time series view of the air temperature averaged over all of North America through time, beginning in 1920 up to 2013. And the black curve is showing you the total or the actual temperature anomaly in this simulation as a function of time. And then after applying the dynamical adjustment procedure, we get the circulation residual or magenta curve. And what you can see is that we've reduced quite a bit the interannual variability of this time series after applying the dynamical adjustment. So it's a lot easier to detect and to quantify the amount of warming that has happened in the last several decades. So as I said, in a model ensemble such as this, we know the true forced response. That's simply the ensemble. So I'm showing that to you in the red curve. That's the true forced response. And you can see that the magenta curve has a very close resemblance to the forced response. In other words, we really are getting much closer to the true radiatively forced response or anthropogenic effect when we remove the effects of dynamics. And then what's left, of course, is the internal component, total minus force, that's shown in the blue. And again, you can see that the intraannual fluctuations in the internal component look a lot like the intraannual fluctuations in the total. And that's what has been primarily removed through this dynamical adjustment procedure. But the blue curve does show a hint of warming in the last few decades. So part of the warming is actually internal to the climate system rather than induced by anthropogenic effects. So here I am going to show you maps now of the air temperature trends over North America for the last 50 years when we have actually seen warming in this particular simulation. So again, these are the wintertime air temperature trends over the last 50 years, roughly. The observed temperature trends from the Berkeley Earth surface temperature data set are shown in the upper left panel, and simulation number 7 from CSM is shown in the middle. And as I said before, I picked this particular simulation as an example of how realistic the model can be in terms of its air temperature trends. But keep in mind that each of these maps is the total trend, i.e. a combination of internal influence and radiative forcing. So you might say, okay, the model is perfect. We can stop here. Well, here's picking another example, another simulation, same model, same radiative forcing, and we get a very different depiction of trends over the next 50 years. In fact, there's even cooling over parts of the western part of the continent. And this has to be due to internal variability, since the force component is the same as simulation number 7. So what happens when we dynamically adjust each of these simulations and the observations? So the lower row is showing you the same observations and the two simulations after applying dynamical adjustment. So removing the circulation-induced component brings the three sets of maps into closer alignment. They all show more evidence of this poleward amplification towards the Arctic and also around Hudson's Bay. They have slightly different amplitudes, but they are much closer together than in the total field. So dynamical adjustment is bringing them into closer alignment. If I show you the forced response from the model, that is the average of all 42 ensemble members, that's now shown in the middle, bottom row. That's by definition the radiatively forced response in the model. That has a very much closer correspondence to simulation 25 after dynamical adjustment, and fairly close correspondence to the observations. In other words, dynamical adjustment is getting us closer to the forced spatial pattern of the anthropogenic response, the counterpart of the time series that I showed you a moment ago. Now, of course, we can also take the CMIP5 models, all 38 of them, and average those together, and that gives us another depiction of the radiatively forced response. And shown here on the lower right, it has a slightly larger amplitude than the forced response from the CSN1, but the pattern is very similar. And again, very nice correspondence with the observations. And then finally, this area over Western Canada, which has witnessed almost 4-degree warming in the last 50 years, we can start to dissect the contributions to that warming. And we find that after dynamical adjustment, the warming is actually cut in half. In other words, circulation-induced effects, which are primarily internal to the climate system, were responsible for roughly half of the warming over Western Canada. The forced response from these two different model ensembles show us roughly somewhere between 1.6 and 2.2 degrees of warming, roughly in the ballpark of the dynamically adjusted observations. So again, collectively, all the results are pointing to the power of removing the circulation through dynamical adjustment to better reveal the forced response. More generally, we can look across all 30 members of the large ensemble. When I made this slide in a publication, we only had 30 members to work with. That's why I'm showing you 30. And again, looking at now both the sea level pressure trends and the temperature trends over the last 50 years. So it's a lot to look at. I'm not asking you to look at details. Each one of these, if you will, postage stamp size maps is showing you the air temperature trends in color, and the contours showing you the sea level pressure trends. The point is just to see that there's a mix of reds and blues in any single simulation. After we apply dynamical adjustment to each one of these ensemble members, there is much more homogeneity in the maps, and there are almost no contours left, meaning that almost all of the circulation effects are actually accounted for in our dynamical adjustment procedure, and in so doing, we have reduced the spread amongst the ensemble members. And again, just a before and after dynamical adjustment comparison, you can see that we've really reduced the spread very sizably after applying this procedure. And in fact, you can quantify the spread through standard deviations of these maps, and on average, at each location, on average, over North America, the spread in air temperature trends is reduced by 75%. The signal to noise is increased from 1.3 to 2.3 on average, So again, now we're really in a much better position to identify the forced response after dynamical adjustment because we have signal to noise that exceeds 2. And then time of emergence of the anthropogenic warming actually advances by 1 to 2 decades on average. Very quickly, I'll show you the time of emergence from this model ensemble, the decade when the forced trend exceeds the amplitude of the internal variability by 2 standard deviations. Much of the western part of the continent has actually not yet emerged by this definition by 2013. However, after applying dynamical adjustment, because we reduce the noise, we actually advance the time of emergence, detection, and in fact, the whole western part of the whole country is now emergent. And as I said, it advances by 1 to 2 decades on average. Okay, last part of the results from this presentation, using observations to constrain climate change projection uncertainty due to internal variability. It's all fine to use models, but really can we trust the model's internal variability? That's really at the heart of this whole exercise. And we should really, really scrutinize our models for their ability to have a realistic depiction of internal variability. So here's another way forward. We can actually use the observational record to get a sense of the uncertainty on the amplitude and pattern of the trend in the future just from the statistics of the interannual variability. So in a Thompson et al. Paper from last year, this was done analytically, looking at the amplitude of the internal variability, and one is able to scale the interannual variability up to look at the uncertainty in trends of any length. So it's a very powerful method. This was recently extended, this methodology, to look at the patterns of the noise. And as I've shown you earlier, it's very important to get the patterns right because the atmospheric circulation imprints very large-scale patterns of internal variability. So I'd just like to show you a couple of examples from this work. And in a sense, it's the counterpart of the model's large ensemble, where we construct a large ensemble just based on the observations. So I said I would come back to this notion of climate noise being the roll of the dice once you're beyond the predictability time horizon. So here what we've done is we've preserved the statistical properties of the observed interannual variability, first removing the forced response as given by the models, and then taking the statistics of the residual variability, retaining their temporal autocorrelation, variance, and the spatial patterns, but randomly shuffling the data in time so that we get different sequences of internal variability. This is the counterpart of the large ensemble from the models. Then we can add back in the forced response from model ensembles. We can use the CRIP5 ensemble average. We can also use the CSM large ensemble and any other large ensemble that comes online in the future. And we've tested our methodology against the CSM large ensemble where we know the truth. And we find that at each grid box, we actually get errors, methodological errors, less than 20%, and in mid-latitudes actually more like less than 10% at each grid box. So it's actually a very, very precise method. So I'll just give you a flavor for the kinds of things that now we can do with such an observational large ensemble. We can make these postage stamp maps again, trends in the last 50 years of wintertime air temperature. And this is now constructed from the statistics of the observations, and then it's superimposed on the radiatively forced component of the response, given in this case by the CSM1 large ensemble. And again, you can see a variety of spatial patterns. Each one is consistent with the superposition of the internal variability and the anthropogenic influence on climate. So the observed actual trend is shown here in the upper left. And remember that from a few slides ago. Then in this 1,000-member observational large ensemble, I'm showing you the 95th percentile range. The coolest member on average over North America shows cooling over the West Coast. And the warmest member on average over North America shows high amplitude warming centered over the eastern half of the country. Both of these could have occurred had a different sequence of internal variability unfolded. It just happened that we had the one that we actually witnessed, but that doesn't necessarily have to be the case. Now we can compare our observational large ensemble with a CESM1 large ensemble, and again, no need to look at details, but you can see that there's a similar type of pattern and blues and reds coming into both, although you can see more blue in the model large ensemble, suggesting that it has overestimated the amplitude of internal variability. And then if we look at signal to noise as a way of summarizing the results, you can see that the model is actually quite similar to this observational large ensemble, maybe a little bit lower in its signal to noise, but the pattern and the overall amplitude is actually very similar. So the model is actually doing quite well. And in terms of precipitation, I'm showing you here, again, the model may be slightly overestimating the signal to noise relative to the observed large ensemble. But the important thing here is for precipitation, all the values are less than 1, unlike temperature, where in some places they exceed 1, maybe even getting into 2. So precipitation has a much lower signal to noise. In the interest of time, I'm going to have to skip through these last few results very quickly. But again, with this observational large ensemble, we can look globally at the terrestrial surface climate, and we can make maps of signal to noise in the last 50 years and the next 50 years, assuming the variability does not change. It does change at high latitudes of the northern continents, but other than that, we find very little evidence that it significantly changes. So these are just some of the types of maps that we can make from the observational large ensemble. Some areas, such as the tropics, have higher signal to noise than mid-latitudes. Last point, limitations of the observational record. We have roughly 100 years of observations on which to build this observational large ensemble. Is that enough? So I come back to our namesake, Bjerknes, and the example of ENSO. So the question is 100 years enough to constrain the statistics of the variability? So here are the observed standard deviation of sea surface temperature roughly the last 100 years, with the Nino 3.4 SST time series shown below in the box highlighted in the eastern equatorial Pacific. Here's run number 13 from the CESM1 large ensemble. It actually does a very nice job of getting a realistic amplitude of variability of ENSO and also a very realistic power spectrum in terms of the Nino 3.4 index. However, number 14, you can see a much larger amplitude of variability in the equatorial Pacific. And of course, this is something you cannot get from 100 years of observations. We just don't have another 100 years at this point. So we have to always bear in mind that the 100 years that we have may not necessarily be sufficient to constrain the statistics of the observed variability. If you'd like to know, have a simple way of finding diagnostics of these patterns and modes of internal variability, I point you to the climate variability diagnostics package at NCAR, and also a very nice community resource called the Climate Data Guide, which is a international effort to collect the wisdom and experience of data providers and users to bear on many hundreds of climate data sets. So I hope you find these two community resources useful. So I wrap up in the next 2 minutes, summary and outlook, very broad brush take-home points I'd like to provide. Number one, expect a range of climate trends on these local regional scales over the next 50 years due to the superposition of the greenhouse gas force response and internal variability. Number two, the spread in 50-year climate trends within a single model is mainly due to unforced and unpredictable atmospheric circulation variability, especially at middle and high latitudes. Number three, this internal atmospheric circulation variability must be taken into account when interpreting observed climate trends. Number four, utility of large ensembles. They're useful for defining the forced climate signal on local scales. Once you have that, you're able to compare models in a productive fashion and also to properly compare models with nature. Number five, similar points can be made regarding dynamical adjustment. And in particular, dynamical adjustment is useful for revealing the forced climate signal on these local scales for comparing models and comparing models with nature. And last, evaluating internal climate variability in models is paramount. Need to take into account the limited sampling of the observational record, and I hope that this idea of an observational large ensemble will gain traction and that many of you will work on extending the scope of this observational large ensemble. And with that, thank you very much, and I will then take questions via Skype. Thank you very much, and also I hope that many of you will avail yourselves of the CESM1 large ensemble. Thank you.
Okay, thank you very much, Clara, and through the magic of technology, we can now welcome you into the lecture hall. We only have a couple of moments, but I know that Clara would love to have a question or two. If you have a question, it's absolutely necessary for you to come up to one of the microphones to ask a question. So let's take a moment or two for a question for Clara before we move on to the Charney lecture. Yes, come on up.
Clara, this is Hong Hai from Princeton University. I have a question about the observational large ensemble. It is, if I understand you correctly, it is constructed by adding the internal variability from observations to the forced response estimated from the CSM large model ensemble. So I guess I don't quite understand what kind of new knowledge we can get from this observational large ensemble besides what we already learned from the CSM large ensemble.
Well, we never know with the model if the model has a realistic depiction of the internal variability. So we really shouldn't trust models at face value. We really want to use the observed statistics to get a much more, by definition, realistic estimate of the variability. So that's the bottom line.
I don't know, this is Mike Pritchard from UCI. I had another question about the observational large ensemble. Sort of fascinating how the Great Lakes region popped out as a place where we should be less worried about internal variability swamping future changes in a way that wasn't as evident in the model. Do you have thoughts on that, or what's missing, or what's going on?
I guess I have to think back if it's not evident in the model, but I think that is a region also in the model where the effects of sea ice cover in Hudson's Bay has a strong kind of lake effect, if you will, on the surrounding regions. And I think that that's why it has a more, a higher signal to noise than some other regions.
Okay, thank you very much. Everyone, please once again join me in congratulating and thanking Clara. Okay, we're going to continue on with the Charney lecture in just 1 or 2 moments, so don't get too disruptive, don't leave. We just have to do a little bit of technology switching here, so we'll be with you in just a moment.